that probable location starts to become where the material is at, almost.
Yeah, I see what you're saying. So yeah, in another visual model that we use when describing these crystalline solids, these materials, is sort of these ball and stick models, where we have like a bunch of balls connected by sticks, making like a regularly repeating structure. And this is a common visualization tool. Many older professors have them in their offices. Back from when you didn't have the luxury of digital tools to explain the same concept.
Or even if you even if you do like an AFM scan, right, of a surface, you kind of see this, right? It seems like it really is a surface that appears at that, where the 99.9% of probability of the electron shell is located at. It's like,
yeah, I would say yes and no. So like in our macroscopic world, we kind of, the surfaces we deal with are kind of more absolute. So like the surface of the table in front of you, it's kind of a very rigidly defined surface. I don't know if you can smash your hand through it, but it won't be easy. So that's kind of our intuition of surfaces. But in the world of atoms, it's not quite so such a hard cutoff. So, for example, in materials, they're not literally hard shell spheres. So if you have a certain material, you can mush the atoms closer together. It's not easy, but you can stick the material between two diamonds, and you can make that happen. And also, when you raise the temperature, usually materials expand. So then the effective size of your balls appears larger, but this just kind of reflects the fuzziness of this electron cloud.
But it does seem to act sort of like a pressure boundary in that sense. Like when you squeeze them, you have to displace all of, I don't know, it's like almost like you have to displace that surface. Maybe, with turboelectricity or something, you're actually spooling up the electron somehow in doing that. It's like, it's interesting how they do form some sort of effective surface in the context of various physical interactions.
Or at the very least, it seems like it could be modeled as one.
Yeah. So, I guess there is sort of an effective size of the atoms. And I would say a more realistic model than just like hard balls bumping against each other is you can have hard balls, but then springs between them. So sometimes the models in the old professors' offices, they will have the balls on springs. And that, I think, is the more accurate visualization. So you can sort of push them together and pull them apart a little bit. And that is actually pretty accurate. And like in a material, the atoms, they're not literally on springs, but this kind of gets to a really cool thing about physics, or a not cool thing if you don't get concepts the first time around. But in physics, like we kind of learn the same thing over and over and teach the same thing over and over in every class and every subfield. And one of these themes that we come to again and again is something that in physics we call a harmonic oscillator. If it's quantum mechanical, it's a quantum harmonic oscillator, but it's just a spring. And the reason that this shows up over and over and over is because typically systems, and I don't just mean materials, I mean like almost anything, it's going to be in some energy minimum. And usually it's possible for it to move away from its energy minimum somehow, raise its energy a little bit, and do it along different coordinates. So the potential energy landscape that it lives in is similar to that of a spring. So going back to the model of a material as these balls on springs, So that is a pretty good model, at least of the atoms, because each atom, it sort of sits in an energy landscape that looks like that of a spring. So mathematically, it's very similar to a spring. There aren't literally springs, but for all effects and purposes, you can really quite accurately visualize it that way.
I think that a mathematical Zen koan would be like, if it acts like a spring and it looks like a spring, can you call it a spring? But I totally understand what you mean. Like, there's not actually like the spring structure down there, but what does it mean?
Well, it's like, I mean, all of my PhD was in elastic mechanics, and I worked a lot with the AFMs and so forth. And it just, the more I started studying quantum mechanics, the more I had a hard time not seeing atoms as fundamentally elastic structure, like elastic materials of some sort. The equations are so similar to various elastic mechanics, especially when you get into the torsional aspects of the AFM and so forth. You just start seeing these similarities in the behaviors. And so I think that it's, it is a great analogy, but I think there's something there too. Like, I think there is something elastic about the atom, which is interesting.
Yeah, absolutely. So I guess, there's like verbal analogies that people sometimes use that are almost by definition incomplete. However, when the analogy is not verbal but mathematical, I think that is where you can sort of exploit universalities of nature. So you get very similar looking equations in a lot of different contexts, and in that case, if you can solve the equation, you can solve the equation, and you can take it as far as it goes. So one example of like math that shows up everywhere is things that look like springs. So that kind of math shows up everywhere, with pendulums, with actual springs, with atoms in a solid, and so on and so forth. Many examples. Another type of equation that shows up in a lot of places is waves. So like you have wave-like particles in quantum mechanics. Maybe that's not the best place to start. You have like pressure waves in air, also known as sound. You have waves in water, obviously, and you can use the same equations. Plucking a guitar string, so you can use the same equations for all of those, and at some point you do need to consider the specifics of the different types of waves, but you can take this mathematical analogy as far as you can. It's not really an analogy, it's sort of a common description of different phenomena.
Yeah, the transport phenomena are another good example of that too, like heat flow and momentum and things like that, diffusion. It's striking how similarly nature quantitatively reiterates itself over and over and over again.
Yeah.
Well, that's one of those things that leads people to think that we live in a